Well, today's topic is solids. We all know a lot about solids just from physical experience, but we're going to learn some things probably that you didn't know before about solids, some ways that they can be mathematically described in some of the phenomena that we're familiar with, like how they respond when you pull on them. Well, let's get started. One property of solids is shared with liquids, and that is that they are incompressible. When the pressure goes up, the volume really doesn't change that much for solids, which is also true for liquids, as we saw earlier. For gases, whole different story. As pressure increases, volume or decreases dramatically. Solids have a definite shape. This is unlike either liquids or gases. When a solid is in any kind of a container, doesn't matter where it's put, its shape will stay the same unless you actually break it. Another property of solids that's related to their ability to maintain their own shape is called tensile strength. The word tensile has a word part in it that we recognize from tension, and in fact those two concepts are related. This is strength when the solid is in tension. In other words, when you pull on it, it can pull back. That's tensile strength. The tensile strength of each solid is going to be different. It's going to depend on its chemical properties. But this is a relationship that can relate tensile strength to something measurable. If we pull on something until it breaks, that force that it takes to break it, call it the force breaking, divided by the area, that's going to be the tensile strength. So in units, this would be newtons, and the area would be measured in square meters. And sometimes it's also called pascals, as you know. So those are the units on tensile strength. Well, here's an example problem. Tensile strength of platinum is 3.5 times 10 to the 8th newtons per square meter. You can see it's a very large number. It takes a lot of newtons to break something that's a square meter in area. What force would be needed to break a platinum bar that's 2 centimeters thick and 8 centimeters wide? Well, here's our platinum bar. We can think about this platinum bar as having a cross-sectional area. And that's the area that we're talking about in the tensile strength equation. So this is 2 centimeters thick, and it's 8 centimeters wide. Well, 2 centimeters in meters is going to be 0.02 meters, and 8 centimeters is going to be 0.08 meters. And so the area of this cross-sectional area of this platinum bar is length times width, which is 0.02 meters, times 0.08 meters. And that area comes out to be 0.0016 square meters. So if tensile strength is breaking force divided by area, well, the breaking force is tensile strength times area. So we'll take the tensile strength of platinum, 3.5 times 10 to the 8th newtons per square meter, and we'll multiply that by the area that we just calculated, 0.0016 square meters. The square meters drop out of this equation, and we'll just end up with a breaking force in newtons, which is a unit of force, and it's 896 newtons. Another property of solids is called ductility. Ductility is the ability to be drawn or stretched into a longer, thinner shape. Like here we see in a schematic, sort of a cartoon, of drawing wire. Wire is made by taking a thicker wire, a thicker cylinder, passing it through a die made of a stronger material, and then just pulling on this end with some pretty large force, and that causes it to just stretch, so it becomes thinner and longer. This is an example of what's called punch and die work. All of these pieces that look like cans they originally started out as flat sheets of metal, and they were just punched together by a thing called a punch that's sort of shaped like the can itself, and it stretches it out, kind of like if you punched your fist into a big sheet of rubber, except rubber's way more elastic, so this will eventually stay. So that's ductility. And there's also malleability. That's the ability to be hammered, rolled, or pressed into a different shape without breaking, without cracking up. And the two are sort of related to each other. Here you see a blacksmith pounding on this metal strap here, and the metal strap is taking a new shape as he pounds on it. That's malleability. As solids go, metals tend to be pretty good at malleability and ductility. They stretch well, they pound well, and non-metals tend to be not that good at it. They have poor malleability, poor ductility. The ability of a solid to return to its original size or its original shape after external forces are taken away from it, after it's been stretched a little bit or even compressed or twisted, that's called its elasticity. And different substances have different elasticity. It depends again on the chemical makeup of the solid. But we can again describe this using some mathematical equations. To talk about the details of elasticity and quantify it, there are a few terms that we need to define. One of them is stress. Stress is not like what makes you have a headache or something like that. Stress in physics is the ratio of force to area during a shape change. So think about our platinum bar. In the other example, we had a cross-sectional area, and that bar was under a force. It's being pulled on by some force. The ratio of that force to the area over which that force is applied, well, that is what we call stress. Strain is a measure of the relative change in shape. Now, to get at this idea, let's imagine we have a bar here made of some solid of length L. You can see it's got an initial length L there. And we subject this to a force. What happens? Well, if you pull hard enough, the bar is going to get longer. It's going to elongate. Here's what strain is. Strain is another measure here, and it's equal to the ratio of the change in length to the original length. So if this is an inch long and it changed by 1/1000th of an inch, the strain would be 1/1000th over 1. There's another way we can think about strain. Imagine that we have a bar like the platinum bar that we were talking about earlier, and this is its cross-sectional area that we're looking right down at the front of it. Now, if we had a force that wasn't applied so that it was pulling on one side, but a force that was pushing on one side, and this was anchored down here, so imagine that you have this force that's pushing up at the top of this thing, and somehow this is welded to something really, really heavy, or for some reason the bottom can't move. As we put a force on here, this is going to deform like this. And it's going to bend over at the top. That action is called shear, and how much it gets sheared over is called the shear strain, and that's quantified with the same equation. Shear strain is delta L over L. Again, now delta L is how far did the top get moved over, and L is the length of the original block. Now, if you take a look at this angle here that's been created, how far it's been twisted over, there's a relationship between delta L, which is the opposite, and L, which is the adjacent, and of course that is the tangent of theta. So another way we can say it is, for shear strain, we could say it's delta L over L, which is equal to the tangent of theta. One place where we commonly see shear strain is when a rod or a shaft is in torsion, in other words, being twisted. So imagine this is a rod, this is just the end of the rod, and it's got a twist on it, like maybe it's a bicycle crank and somebody's pedaling it, or it's a crankshaft in a car. For some reason there's some torsion on it. Well, if it gets locked in place, you're going to bend that thing a little bit. Not bend it, but you're going to twist it a little bit. If this end is anchored and it can't move or it's stuck, you can bend it through some angle. And the strain, for an example like that, for torsional strain, that could be measured again as the tangent of the angle through which this twists. Well, there's a relationship between stress and strain, and that relationship has a name. It's called Hooke's law. Hooke's law says, in English, it says, within the elastic limit of a solid, strain is proportional to stress. Now here's what that means. There's a limit to how much you can stretch something and have it go back to its original condition. And it's given in this graph. This is stress here, so in other words, that's how much you've pulled it, how hard you've pulled it. And this is strain, which is how much it got stretched. And there's a nice linear relationship for a certain period here of stress. As long as I don't go past that point there, which is called the yield strength, I can pull it and then let go and it'll go back. If I put more stress on, it'll go up. If I take the stress off, it'll go back. And it'll just keep oscillating back and forth. Stress is proportional to strain. Once you get past the yield strength, however, all bets are off, and you reach a sudden increase in length. You see the strain is rapidly increasing, where the stress just pretty much stays constant or even goes down a little bit. And then you have to start pulling again. The stress goes up, but not linearly anymore. And then it reaches this one maximum strength where you're not going to have to put any more stress than that on this piece of material. And then the stress starts to drop off as it gets longer and longer, and then pretty soon it just breaks. It's the fracture point. Well, in this zone here, this is the elastic limit. This is stress, and this is strain. And that's the slope of this line, because that's rise over run. So Hooke's law says that stress is proportional to strain. And the constant of proportionality is this constant that's called Young's modulus. So Young's modulus is the ratio of strain to stress within the elastic limit. So we could say Young's modulus is stress over strain. But now we know what stress is. Stress is just the ratio of force per unit area. And we also know what strain is. Strain, for elongation strain, let's say, is just delta L over L. So that means that we could simplify this a little bit, and we could say F times L over area times delta L is Young's modulus. And as you might imagine, Young's modulus becomes a powerful problem-solving tool that can be used to solve all kinds of problems as long as you're within elastic limits.